Right. So when you have a tension problem, what you have is an object. The object is suspended, which means it's not moving. And one initially might think that because it's not moving, there are no forces acting on, and that's not true. What you have is you have several forces acting in opposition or opposite directions to each other, and they all cancel out, and therefore the net force is equal to 0. And so what you have is you have the sum of all of the forces in the x direction is equal to 0. And if you add up all of the forces in the y direction, you are again going to get a total of 0. And so as we approach this problem, what we wind up doing is we wind up solving for all the forces in the x direction, and we wind up solving for all the forces in the y direction. And so what we have is this force going this way. Now, how do we know that force is even there? Well, because you have this tension in the rope going this way, and there is an x component to that force. Now, you have also a force in the y direction. Once again, because that tension coming from here has a y component. And the force in this direction is the F in the x direction positive. This was a force in the negative direction. And you also have a force in the y direction going this way. Now when you look at these tensions, you may say, right, there's a force in the y direction, force in the y direction. What is counteracting these forces in the y direction? The answer is there's a force due to gravity coming down this way, and that force is 5 newtons. Now what it's asking us to do is it wants us to find the angle that exists right here. So this angle is ultimately what we're looking for. But in order to solve that, what we have to do is we have to solve this force in the negative x direction. We got to solve for this force in the y direction. We have to solve for this force in the positive x direction. And we have to solve for this force in the positive y direction. So if we're saying, what exactly are we solving for here? We're solving for 1, 2, 3, 4. We're solving for 5 items. And that's how we got to approach it. Now I'm going to designate this stuff on the left side as onesies. And I'm going to solve for this stuff on the right as twosies, because it simply lets me keep it all straightened out. So looking at this, we have a right triangle. And I want to solve for the f of x1 this way. Well, in order to do that, if I take the cosine, which is adjacent over hypotenuse, and the hypotenuse is the tension here, I can solve for the f of x1. So notice what I'm about to do here. It's kind of a nice organizational tool. Is I'm going to solve for f of x1. I'm going to solve for the f of y1. Hope it stays. I'm going to solve for the f of x2 and the f of y2. And I'm going to solve for the theta value here. And just for kicks, I left it off. There is this tension here. I'm going to solve for T2. Now this is a very helpful design. What I've laid out here is I've laid out what exactly I'm going to be solving for. It's an organizational tool. And again, the genius of Sir Isaac Newton on so many levels was he realized that what one does is you solve for all the forces in all the directions. So let's begin now. I got to solve my f of x1. We're going to do a cosine. So we're going to set it up as f x1. And so what we're going to do is write down my notes organized here. What we're going to say is that the f of x1 cosine of my degree, which is 31, I'm going to multiply that times 76. Now the reason why I do that is because cosine of 31 is equal to opposite, which is my x value, over hypotenuse, which is 76. If I rearrange that, I get cosine 31 times 76. And what I wind up with is I wind up with a 65.14 newtons. So this value is negative 65, but that's in the negative direction. So it's going to be a negative 65.14 newtons. Cool. Now, what is the f of y in this direction? Well, that's going to be the opposite over hypotenuse, which means I'm going to use the sine of this. So let's solve now for the f of y, which would be sine 31 times 76, which is going to be equal to 39.14 newtons. Now this is in the positive direction, so we're going to keep that as 39.14 newtons. Now we're going to tackle the right side. Now, in order to tackle the right side, what we're going to need to do is recognize that the force to the left has to match the magnitude of the force to the right. How do you know that? Well, because the object is suspended. So all the forces in the x direction to the left and right has to cancel. Therefore, f of x2 is going to be a positive 65.14 newtons, because that's going to balance the other side here. Now, by knowing that, we can now solve for the next idea, which is that we know that the force going up has to balance the force coming down. We know one of those forces going up is f of y2. F of y1. We just solved that. We know the total force coming down is 85. So we're going to be able to say that the sum of the forces going up is going to be countered, if you will, by the 85 newtons coming down. And let's see if we can't fix that just a bit and notice that it is 85. We erased the whole thing. Of course, we erased the whole thing. But we have a force here of 85 newtons. If you look at your problem, that in fact is what was written there. So 85 newtons was a given value, and my clumsy writing blocked it out. So we have 85 newtons coming down. So the F of y, forces in the y direction, have to equal a total of 85. So F of y2 is going to be the following. It's going to be, let's put it over here actually. So what we have is the force going down is 85 newtons. Did the same thing again. Come on, Mr. Kurth, get your head in the game. Alright, so we have 85 newtons downwards is going to have to equal F of y 1 upwards plus F of y 2 upwards. Now this is a nice illustration of how sometimes physics can get a bit dodgy, which is that it's not just find the equation, plug and chug. What you got to be able to do is you got to realize, oh yeah, these forces up match these forces down. Unless you have that realization, it's going to be hard to realize that, oh, I got to punch these numbers in this way. So F of y 1, which we solved over here, is going to be equal to 39.14. And so the result is F of y is going to have to equal, we would move that over there, so F of y is going to have to equal 45.8 newtons. And we do that algebraically here. So F of y2 is a 45.8 newtons. Now, that allows us to now tackle the theta if we choose here. Now, the way we're going to do theta is we know this value, F of y2, there it is. We know F of x2, there it is. So if we in fact to solve for theta, we take the tangent of theta is going to equal to opposite F of y, which is 45.8 newtons, divided by F of x2, which is 65. So, solving for theta, you get 35 degrees. So you come over here and write down now we know theta. The last thing is exactly how much tension is over here on the right. So now we actually could take a couple approaches. We could do the thing using trigonometry. We can also use Pythagorean theorem, where a squared and b squared equals c squared. And just for kicks, let's take that as our approach. So the tension in 2 is going to be equal to a squared plus b squared equals c squared, where we'll make a squared 45.8 plus 65.14. That's going to equal to the tension squared. When you crunch the numbers, you get 76.66 newtons. Now, at this point, sometimes there's an easy confusion. You'll notice that the force coming down is 85, but the tension here is 76. And the, Mr. Kurth, you didn't get your head in the game. Let's try this again. My bad. 79. Attaboy. Okay. So you'll notice that there's 76 newtons this way, 79.66 this way, and you think, but wait a minute. It's supposed to counter the 85. And if you add up the 76 and 79, that's much more than 85. Something's wrong. You think, well, this is at an angle. So the way I think about it is a certain amount of the 76 newtons is being lost or devoted to the x this way. So the 76 going up is obviously less than that. And the total tension here is 79, but that's being split between the x direction and the y direction. So you don't get the full effect, if you will, of the 79. So these numbers on the tension won't exactly match the vertical downwards because it's being distributed among the two directions. So the other thing to observe is, one, because the system is in a suspended state, the total force, the total F of x and the total F of y has to be equal since the total force is 0. So we have to divide the problem in two parts. The other thing to realize is you have to identify what are the forces that are acting on the system. And we nicely listed those out right here. And that then said, right, if you want F of x1, well, let's use this mathematical trick. If you want F of y2, let's use this trick. So once you list out what I'm looking for, you come over here and you start to punch these numbers out using all kinds of different trickery. But I knew I needed to work it out because I created a list right there.